All right, high school physics. We're going to move on to a new concept today that I think you're going to find to be pretty easy. This is gravitational potential energy. Okay, so this is another type of energy we're going to look at today. Gravitational potential energy is all about potential energy. It's all about stored energy. The potential to harm is a good way to kind of think of potential energy. If you have a brick and you hold it up in the air above the earth, if you drop it, it's going to hurt when it hits you, right? Because there's energy stored in that brick when it's above the surface of the earth. If you drop a brick from 10 meters up and it lands on your toe, that's going to hurt a lot more than if the brick was only 1 meter off the ground. So this gravitational potential energy, the potential energy is stored energy. Gravitational has to do with this gravitational force that wants to pull objects toward the ground. So related to specifically the earth. So stored energy in an object based on its position above the Earth's surface. That's how we would define gravitational potential energy. Now the formula, this is really easy. Gravitational potential energy is equal to the mass of the object. Think about it. The heavier the brick is, the more energy it's going to have when it hits your toe. G, so the amount of gravity, that acceleration downward due to gravity, that plays into it also. And not only is the mass and the acceleration due to gravity, but also the height of the object, how high it is above the earth. So this is one of our easiest equations. You just multiply mass times gravity, as in acceleration due to gravity, times the height. Now the units, if you think about it, force of gravity, mg, is usually measured in newtons. Think about force of gravity, which is equal to mg. That's usually measured in newtons. So this piece of it right here is newtons, and then height is going to be in meters. So it should be newtons times meters. So the units are going to be Newton meters, or more commonly, we're going to use the unit what's called joules. Joules really has to do with energy. And so we're going to stick with joules, although Newton times meters is perfectly acceptable here. All right. Now, how do we get an object to that height above the ground? Well, we have to pull on it, right? So think about the fact that if you have this box and you want to lift it upward, but gravity is opposing it, you're going to have to pull upward with a force that opposes the force of gravity. And you're going to have to pull with at least that force of gravity upward, right? So when you think about work, we talked about work already. The main formula we use for work is what force are we using times distance. Okay, well, the force we're going to have to pull with here, this force of tension, has got to be equal to the force of gravity. So force of gravity is the amount of force we need pulling upward times distance. Well, think about it. Force of gravity is just mg. And when we're talking about distance upward, we're actually talking about that change in height. You're going to see the formula really written like this. Change in height. What do we mean by that? Well, if we have an object, we think about its initial height and its final height, and we find the difference between here and there. If we can find that change in height, that's what delta H is. And most of the time, assuming we start the object at ground level or at zero, that height that we pull it to is also equal to the change in height. So you're going to find very quickly, look how close these formulas look to each other. The work we need to lift an object up to a certain height is actually equal to the potential energy it's left with after we get it to that height. So those really are the same. When I think about moving an object upward, I have to put work into it, a force times a distance or height. That's actually equal to the amount of energy it ends up having stored in it. So our work lifting upward is equivalent to the potential energy it's left with afterwards. Same thing with units. The units are going to be joules or Newton meters. Typically, we're going to try to stick with joules as we're going through this. Okay, so pretty easy formulas, and let me do a couple problems with you that I think you'll find to be pretty easy. Let me do two sample problems with you. Here's our first sample problem. It says A 12 kilogram box is lifted to a height of 6 meters above the ground. We're going to calculate the work required to lift the box, and then we're going to find how much potential energy it has after it's lifted. So here's my picture. I've got this box, and I'm going to lift it upward a height of 6 meters. Okay. So think about what we have. We have a force pulling upward. The work required to lift an object upward is really equal to the force of gravity times that change in height. Or more simply, we would just take the mass times g times our change in height to find that work. We know the mass of the box is 12.5 kilograms. 9.80 is acceleration due to gravity, and the height we lifted to is 6 meters. So we punch this into a calculator. We take 12.5 times 9.80 times 6.0, and you're going to get 735 joules of work that we put into it. By lifting it up, we're pushing it upward or pulling it upward. We're needing 735 joules of work to go into it. Well, if we do that, what's its potential energy going to be at that highest point? So when we're finished, how much potential energy does it have? Well, hey, look, the numbers are going to turn out to be the same thing. Once we lift it from the ground up to that 6 meters, we really have the same calculation. 12.5 is the mass, 9.80 times the height we lifted it to is 6.0, so 735 joules of energy it now has in the form of potential energy because we lifted it to that height. So the work we put into it turns into gravitational potential energy, okay? All right, last problem, and I think this is a good application style problem to talk about, is we have a box, and it says the box is pushed up a 15-meter ramp to a height of 7.50 meters. I'm going to see if I can give us a little bit more space here. 7.50 meters above the ground. How much work? It should say how much work. How much work is done if the box is pushed with an applied force of 245 newtons? Okay, how much work? Having trouble here. It says how much work is done if the box is pushed up with an applied force of 245 newtons. And then how much gravitational potential energy will the box have at the top of the ramp? Then we're going to recalculate how much work would be required to lift the box straight up to that same height. So if you're having trouble visualizing what's going on here, here's what we're talking about. We've got a ramp, and we put a box at the bottom of the ramp. And we're going to push the box up the ramp with an applied force of 245 newtons. Okay. The other thing we know about the ramp is it has a distance from here to here of 15 meters. That's the distance we're going to push it up the ramp. Okay. And when we are finished, the height of the ramp or above the ground is 7.50 meters. So let's go ahead and start and do part A. How much work is done if we're going to push the box with an applied force up the ramp? So remember, when we are pushing on a surface, work is equal to force times distance. We're pushing it along the surface of the ramp with 245 newtons. The distance we push it from point A to point B is going to be 15 meters. So we punch this into a calculator to find out how much work is required. 245 newtons times 15 meters. That's going to be 3,675 joules of energy we put into pushing the box. When we get the box at its final position, what is its potential energy? Well, to find the gravitational potential energy, we do MGH. Think about the box. It's 50 kilograms, 9.80 meters per second squared times the height change from where it started to where it ended up. That means the gravitational potential energy is going to be 50 times 9.80 times 7.50. Hey, we get 3675 joules. Hey, that makes sense. To push and put work into it, it's going to turn into potential energy. Okay, now, how much work would be required to lift the box? So instead of pushing it up the ramp, what if we had a box and we lifted it straight up to that same height? Well, how do we do work when we're talking about lifting? It's mg delta H. That's going to turn out to be the same numbers I just put in the problem above. We lifted a change of 7.50. So our work again is 3675. So here's what we find. Whether we push it up the ramp like we did in part A, or we lift it straight up to that same height, both of those require the same amount of work to move the box from the bottom of the ramp to that height of 7.5 meters. And they both would give that object 3675 joules of potential energy. So the question is, why would you use a ramp? What's the point? If you think about like you're working with a moving company, lifting straight up onto the back of a truck versus pushing it up a ramp, what would be the advantage to actually use a ramp, right? So here's what you want to think about. You want to think about the forces, okay? If I'm going to go with pushing it up the ramp, the force I needed, this applied force, was 245 newtons to push it up the ramp, right? That would, I'm going to call this A, okay? So A, I needed 245 newtons. Now I'm going to push it a distance of 15 meters, but my force required to push it is 245 newtons. If I choose this other path, I'm going to call this path B. How much force is required to lift that object up? Well, go back to our work equation here. mg is really our force. That's the force of gravity. So we can calculate that to figure out how much force of gravity we are lifting with. We would take the mass of 50, multiply it by 9.80, and we get 490 newtons of force that's needed if we lift straight up on it. We're basically pulling with a force equal to its weight. So what's the advantage? Why would we use a ramp? Well, look at it. The ramp only requires 245 newtons of force, whereas lifting straight up required 490 newtons of force. So pushing up the ramp is easier in terms of the amount of force that's needed. That's one of the advantages of using a ramp. And when we talk about mechanical advantage in terms of simple machines and things like that, that's really what it comes down to, is comparing the lifting force comparing to the pushing force. Pushing force is half the amount. So it gives us twice an advantage in terms of force using a ramp.